So, hi everyone, welcome to the fourth and last lecture by Flaminia Giacomini. She's been teaching us this week about quantum information tools at the interface between quantum theory and gravity. As you know, we have her slides and the video of the lectures on our website. It's going to be posted later in the chat. And as usual, please feel free to ask questions during the talk. You can raise your hand and then I can ask you to unmute yourself and you can ask the question directly. Otherwise, you can ask in the Q&A chat. And as usual, we're going to have a longer time towards the end of the lecture for more discussion. All right, I guess you can start, Flaminia. Thank you.
Thank you very much. And thank you to all of you who have stayed until the very end, the very last lecture. So this lecture is on quantum reference frames. So after we have looked at theory-independent approach, the process matrix framework, then we looked at the gravitational physics of quantum objects, quantum clocks. Now we get to the last topic, where we're going to see some. So I'm going to take a specific approach. I'm going to focus on a specific approach to quantum reference frames. And I'm going to tell you about some results that we have obtained within this approach. And then at the very end, I just wanted to spend a few minutes to connect the different topics that we discussed during these 4 lectures. But first, let me start with quantum reference frames. And so here, the general question that we want to ask is, well, we have already motivated that when gravity acquires quantum features, then we do not have a classical spacetime anymore. And when we do not have a classical spacetime anymore, we also do not have a classical reference frame. And so how do we deal with the lack of a classical reference frame? How do we make measurements? How do we identify an event? And quantum reference frames is a possible answer to this question. And here I'm not claiming that this formalism that I'm going to present is already in the final form or in the is best suited for exactly this to tackle exactly this question. But what I'm claiming is that we are building up from this formalism to so this is basically the formalism in Galilean quantum mechanics. And then the task that we have now is how to modify it, how to extend it in order to describe instead situations in which gravity is in a quantum state. So this can be modified. It's just a starting point. Okay. So before I tell you about the specific formalism, let me just mention that quantum reference frames have been around for quite some time. In particular, there is a historical coincidence in the quantum information and the quantum gravity community. The first paper that was arguing in favor of the quantization of reference frames, and it was even mentioning words like quantum reference frame or quantum reference system. I'm just going to use that. I'm going to use quantum reference frame, but just bear in mind that people sometimes use quantum reference systems. And so the first papers in the 2 communities were from the same year. You see 1967 here and 1967 here. And so basically each community, both the quantum information and quantum gravity community, took different roads exploring how to make sense of some quantum version of reference frames. And typically these 2 research lines have not much in common one with the other. So they just evolved in parallel. But there are some similarities. So again, yeah, there is a diversity of approaches, but in all cases, the idea is to associate somehow reference frames to physical systems and physical systems that are quantum. And some topics that have been addressed, for instance, is how to make sense of the measurement. Relationalism is something that has been important in both communities. So how to extract relational information from quantum reference frames, motivated in different ways, but this is something that both communities had very well in mind. Also the connection to observers. So typically we tend to keep them distinct from observers, but of course the two notions are somehow related, but we do not know yet how to make sense of quantum observers, and exactly how they are connected. In the quantum information community, there has been also some work that instead was focusing on quantum reference frames in terms of resources. So bounded resources versus unbounded resources. And this is not what I'm going to talk about today. So this is just a slide that is meant as a caveat that there are many different approaches and that it would be good to be aware of all of them. I don't have time to go through all of them, but just so that you know that there is a lot to look at, and just don't be confused that sometimes people assign the same name to things that are not immediately related one to the other. But of course, it would be interesting to look at the connection between these different approaches. Okay. So what is a reference frame? So typically, when we talk about a reference frame, we talk about a set of axes and the state of motion that is useful to represent physics. And so, for instance, to fix the point of view from which a measurement is carried out. And then something that we learn in just standard physics courses is that it's true we can choose a quantum reference frame, but in the end, exactly which reference frame we pick is not important, because all reference frames are good for describing the laws of physics. And now imagine that we are just in quantum mechanics and we want to do a reference frame transformation. So for instance, we can perform just a translation or a Galilean boost. And these are usually represented as unitary operations, where, so here you see that I have this exponential with x0 and the p operator. The p is the generator of translations. And the Galilean boost, analogously, is some e exponential v and g operator. This is the generator of the boost that has this representation here. And now what I would like you to focus your attention on is this quantity x0 and v. So x0 is the relative position between the initial and final reference frame. And v is the relative velocity between the initial and final reference frame. In standard reference frame transformations, these quantities are parameters. They're not operators, they're not dynamical variables, they're just parameters. And this corresponds to our abstraction of the reference frame, so we do not assign them any dynamical law, we do not assign them any Hilbert space. And this is something that we will see later we would like to give up. So we want to consider them as dynamical systems, as quantum systems. But now we also know that the quantum systems to which we apply these transformations also have some dynamics. And this dynamics is governed by a Hamiltonian operator. So now, whenever we apply unitary transformation, we also have to transform the Schrödinger equation. And it turns out that the Schrödinger equation is mapped into a Schrödinger equation if I change my Hamiltonian according to this law, where U is the reference frame transformation that I apply. So here I'm just saying that U is a reference frame transformation because I'm interested in reference frame transformations. But in principle, this holds for any unitary operator that I apply to my quantum state. So it's not necessary that this is exactly a reference frame transformation. And in addition, we say that a unitary transformation U is a symmetry of the dynamical law if the functional form of this Hamiltonian after the transformation is the same as the functional form of the Hamiltonian before the transformation.
May I have a question?
Yeah.
So what is the reason why we actually use Galilean boost over Lorentz boost?
Because we are in just in Galilean quantum mechanics here. In special relativity, we would use a Lorentz boost. Here we are considering just usual one particle non-relativistic
Okay, I see.
mechanics.
Yeah. Thanks.
And which is still a relativistic theory, by the way. And okay, so now let's consider this very simple scenario where we have three particles, A, B, and C. And now the approach that we want to take here is a relational approach. So what we want to say is that it doesn't matter where I place this three particle system. I can place it here, 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 doesn't matter. The physics is going to be the same. So the only variables that matter physically are the relational ones. So in this sense, if I have this three particle state, I will have these two vectors. So for instance, from the perspective of C, I have two vectors that are important. That is the relative distance between A and C and the relative distance between B and C. Analogously, if I take this perspective, then only two vectors are important, but these are the relative distance between C and A and the relative distance between B and A. So you see three particles, two relative distances, but these relative distances have, so once I specify these two vectors, I have all that I need. I have all the information that I need, but you see they're different vectors. And this is because I'm just reshuffling the information. So whenever I write down, say, the state of A from the perspective of C, I am implicitly assuming already that I'm choosing some reference frame in this view. And so the state that I write is actually the relational information that I have of A from the point of view of C. Now, the question that I ask is, let us consider now not a classical system, but a quantum system. So what happens if these are not some classical objects that are whose position is sharply defined, but this is a quantum state which has some uncertainty in position, velocity, or any basis. Then the question that I want to ask is, can I center my quantum reference frame on top of this quantum system? Can I attach somehow a reference frame to an object that is in a superposition of some classical states in some basis? So a superposition of positions, superposition of velocities. Can I do something like that? And well, the answer is going to be yes, but let's see how we're going to do that. So specifically, what we want to do is to start from the description of this particle C. So basically, this particle in its relational picture will describe the quantum system A and the quantum system B from its perspective. And then we want to switch to the perspective of the particle A that will describe particle B and particle C. So now this may sound a bit vague at this point, but I will show you explicitly how to do this construction from a perspective that is nobody's perspective. So like the initial perspective that I had with the three rocks all in a quantum superposition, reducing this to the perspective of one of the particles, and then showing you that how to change explicitly from one reduced perspective to another reduced perspective. So we're going to see two ways in which this can be done. First, starting from something like that and just changing, and then recovering the same picture from an outside perspective, basically. So let's see first the reduced picture. Which at least in my intuition, this is the more intuitive one, but then we're going to check that this is going to be the same also from in the other way. So let's start from ABC. And let's start in particular from the perspective of C, who assigns some position XA to A and some position XB to B. And now, if we just invert this vector relation to describe everything from putting A at the origin, we know that we have to perform this change of coordinates. So the position of C from the perspective of A is simply inverting this vector, and the position of B from the perspective of A is going to be XA minus XB minus XA. So this is the transformation that we want to do. Now, let us take C as the origin. So now here I'm drawing it in 2 dimensions, but this is actually a 1-dimensional formalism. So let's center the initial reference frame in some origin that will correspond in the end to C. Let's consider a particle B that is some wave function that is distributed according to this function here. And now let us translate the origin of this reference frame to some position alpha. So in quantum theory, we know how to do it. This is just a translation operator that I had a few slides ago. So I just apply to system B this translation by alpha. And then everything will be given in terms of XB minus alpha. So this is my new relational variable. But now let us imagine that this alpha is not something that is sharply defined, but it corresponds to some quantum state that has, for instance, this distribution. This is just arbitrary. I just pick this one. And now you see that here, and this is the position of some particle A, some quantum particle A. And now you see that if this quantum particle has this type of distribution, there is no single position here that I can pick to say, okay, I translate the origin to the position of A, because I have multiple choices. So what can I do? One possibility is that I take seriously the linearity of quantum physics, and I say, okay, there is no single position by which I can translate, but it doesn't matter. I can just translate by every single position that I have here in a quantum superposition. But then I say, okay, then I know that it is much more likely to find A in this position than to find A in this position. So I weigh my translation by the wave function of the particle A. If I do that, what happens is that I have, instead of this operation. Let's compare them. So first, you notice that here I only had the quantum system B. Here I added the Hilbert space that corresponds to the Hilbert space of the quantum system that I'm using as the new quantum reference frame. So it's a quantum system in whose position I'm centering my reference frame. And say that this phi is this distribution here, is this wave function. In addition, I promoted this parameter alpha to be a quantum operator on the Hilbert space of the quantum reference frame. Now, one question that usually arises is, don't you have ordering problems? No, because you see, these are 2 operators on different Hilbert spaces, so they commute. So this is not a problem here. Okay, so now, this is the core of the transformation. In addition, I need to add this other operator here that we call parity swap operator. What does it do? It realizes this line here, because so far, what we have done is to map the operator XB into QB minus QC. So basically, if I assign this operator XB from the perspective of C, now with this transformation, we just send it to XB minus XC. But I still miss this part of the transformation. So I still want to describe the relational information from the perspective of A, and so I also want to describe C. So what this does is to send XA into minus QC. and also PA into minus the momentum of C from the perspective of A. So overall, what I get is this operator here. This is a unitary transformation. So if I have the quantum state, I can just transform the quantum state unitarily in this way. Let us see the consequences. And let us start with the simplest case that is the spatial translation in one dimension. So now I have my initial reference frame that is centered in C, and I consider A to be in some well-defined position and B in just some arbitrary quantum state. Here I represented it in this way because it's easier, but doesn't matter. Now, I want to move to the quantum reference frame of this system. Okay, so here something went wrong with the slides. So what I wanted to say is that if A was localized as it was, let me just go back to that. Okay, so if A is localized in this position, then when I apply the quantum reference frame transformation of the slide before to this quantum state, then I just put the origin of the quantum state here, and then I describe C as being in minus XA and B as being in, say, XB minus XA. So basically, it reduces to the usual translation as soon as I have a state that is well localized in position. Yes, the slide of the lectures will be available. Let's consider now a slightly more complicated situation. That is when particle A is in a quantum superposition of X1 and X2, and particle B is always in some well-defined position. Again, it doesn't matter, I can pick, so in the end, this formal is really like you can pick whatever state you want, a mixed state, a pure state, an entangled state, a separable state, it will work. The transformation will work. I'm just giving you simple examples. And so now I want to apply this operator here to the state of A and B and find the description from the quantum reference frame centered on the position of A. So now look at this operator, how it acts. So imagine that it acts on this state. When A is in X1, it translates system B by X1. When A is in X2, it translates system B by X2. And everything happens in a quantum superposition. So what we get is that in the final description of A is at the origin, and then B is in X0 minus X1, and C is in minus X1, and plus superposed coherently with B being in X0 minus X2, and C being in minus X2. So one thing that I would like you to notice is that here I started from a product state, and after the transformation, I have an entangled state. So here we are seeing that entanglement and actually also superposition are quantum reference frame dependent properties. And in addition, once I go here, I can also go back with the inverse transformation to my initial situation. So I can just go back and forth from these two quantum reference frames as I want. It doesn't matter. They're just unitary transformations. So now, that's the simplest situation. But actually, we can also come up with additional transformations, and we will see that in a moment.
Excuse me.
Yeah.
Can I ask a question? Because it seems to me that when you have superposition, you have the possibility of interference effects, right? So when you do this, when you do the reference frame swap to, for example, the reference frame of A, you're sort of taking the superposition of A and moving it to the other states in a way, right? Because in the previous slide, like C and B gain superposition instead. Won't you then observe different interference effects in the different quantum reference frames? And that seems like something that should be reference frame independent, the actual observed effects, right?
Okay, very good. Okay, yeah, this question also comes up quite often. So in the end, all observable properties are the same, because what is interference? So interference, to observe interference, you have to fix the state, but you also have to fix the measurement. And then you take so the way you do that, you say you take the trace of the state times the observable. And this will give you the probability that will give you the interference pattern. Now, what happens if I perform a reference frame transformation, a quantum reference frame transformation? I apply some operator S to my quantum state, rho, and this will be the new rho in the final quantum reference frame. Let's call it A. This is E. But then I also have to transform the operator in order to make the same experiment. So if I transform my operator in this way, then you see the probability is the same, but the operator is going to be different.
So the operator gains a sort of gains an effect that cancels out so that everything works out in the end.
Exactly.
Okay. Yeah, so, that makes a lot of sense. Yeah. Yeah.
So basically, if it's true, like once you change the reference frame, entanglement and superposition the entanglement superposition properties are different, but in order to reveal them, you have to make another experiment, not the same one that you were doing in your original reference frame.
I imagine this gets kind of hairy, because then you're going to have to say, okay, now perform the experiment, but do it in a superposition. And then people start getting into the whole, oh, but what do you mean by experiment and observation? And things get very philosophical and complicated.
That's the problem. Yes, exactly.
Okay. Thanks for the clarification.
Yeah. And yeah, so this makes okay, if I wanted to add something, I forgot now. But if I get it, it comes back to my mind, I will say it. Okay, so now what I showed you is the easiest transformation that we can make, the superposition to the transformation to relative coordinates. But actually, we can come up with additional transformations. We don't necessarily have to keep only that one. We can have arbitrarily many of them. And in particular, we focused on those that are called like some superposition. So, okay, this is not good. So superpositions of transformations. And they all have this structure that you see on the slide, namely some unitary operator here. Okay, just bear with me for this slide. Let me see if. Okay, so no, okay, we have to stick with that. So here, this unitary operator here is just a standard reference frame transformation with some parameter alpha I. And so this could be, for instance, a spatial translation, a Galilean boost, the acceleration, the transformation to an accelerated reference frame, or even some Lorentz boost. So we found several of them. And then this is controlled on some cat alpha I, so cat bra alpha I, so on an additional Hilbert space. And this Hilbert space is the quantum state of the quantum reference frame. So for instance, what I showed you, for instance, is the case in which this is position, but it can also be some velocity, some effective acceleration. So we're not, we don't necessarily have to stick to that one. Now, so you see, as soon as you generalize the reference frame transformation to a quantum reference frame transformation, you are clearly doing something to your two-particle Hilbert space. So in particular, one thing that you see is that when you apply a quantum reference frame transformation, you're changing the partition of your total Hilbert space. So it is not immediate to see that these quantum reference frame transformations are actually still a group. So they still form a group of inertial transformations. And that's a property that you would like to preserve because it ensures that you're mapping the same physical situation to the same physical situation, and that when you compose different transformations, you are still doing an allowed transformation. So that's a property that would be important to preserve. And it turns out that you can build a group, and now I will show you this group structure. So what I mean is that if I write this transformation in an exponential form, then the elements that are on the operator that are in the exponent of the exponential are the algebra of the group. And if I look at the commutation relation between different elements of the algebra, they should close the algebra. So basically, the commutator between two operators has to be the sum of other elements of the algebra with some coefficients. And this is not obvious that you can do it as soon as you have elements that so as soon as you write your quantum reference frame transformation as something that lives on the tensor product of two Hilbert spaces, because this will have more non-trivial commutation relations one with the other. So in standard Galilean quantum mechanics, then this is your representation of the group of inertial of some group of transformations. In particular, the elements of the algebra just act on the Hilbert space of what we would call the system B here. So of the system that is not taken as the quantum reference frame. And the group, the Galilei group of inertial transformations for standard reference frames is given by the translation operator, the generator of the Galilean boost. This is the generator of the translation in time, so it's the Hamiltonian, and the central extension of the Galilei group, which is the mass Casimir of the algebra. So it's the mass of the particle times the identity operator. As soon as I add the quantum reference frames to the picture, what do I get? So it turns out that we can still close the algebra, but we have more generators. So in particular, you see here, the elements of the algebra now are objects that live on the tensor product Hilbert space of the quantum reference frame and the quantum system B. So you already see a first difference. And then you have additional, so the structure is the following. So here we don't have anymore just the single generator of translations here. What this becomes is XA tensor PB. So this would be the equivalent of the translation. Then instead of the boost, we have PA divided by MA tensor the generator of the boost that is the same as here. Then we have the Hamiltonians, so the generator of time translation, which instead of having just the one on system B, we have both the one on system A and the one on system B. And then we have these additional three operators where, so these two is a little bit easier to interpret them. So because you see that there is an identity here and an identity here. So this is basically the generalization of this operator here of the mass Casimir, the central extension, where so this one would be, okay, the notation is a bit confusing, but so this one here would be the equivalent of this one, but then you also need to add the symmetric one with the identity on A. And this operator here looks complicated, but it's actually just a dilation operator. So basically, when you apply this element of the group to XA, it rescales the X by alpha X and P by alpha to the minus 1P. And the same holds for this one. And then we have this additional one, this PA tensor PB, that is more obscure, but actually you can see that. So because one important thing that also we would like to preserve is that this quantum reference frame transformation has to be democratic. So we want to treat the quantum reference frame A and the quantum system B on equal footing. So we want to be able to swap the role of the quantum reference frame and the quantum system. So now I would want to go to the quantum reference frame of B too. Why should I just pick A? So we would like this group to be fully symmetric under exchange of A and B. And now we have written this in this way because it's easier to relate it to the Galilean group, because here we have the GB and PA. But actually notice now that we have XAPB. So we would like to have a term that is PA XB, and we have it because we have PA XB here. But then you notice that there is an additional term here that is PA PB. So I could actually rewrite all these generators in a totally symmetric way by just taking XAPB, PAXB, and PAPB. And I could just drop these other things, and I will just have other constants in front of it, but these are just scalar constants, so it doesn't matter what they are. So this is actually something that is needed because we really want everything to be symmetric and close the group. So this is the group.
Yeah, I have a question.
Yeah.
So these quantum reference frames, they have a specific Hamiltonian, or they can have any Hamiltonian?
No,
because
any Hamiltonian.
Any Hamiltonian will work for them.
Yeah.
Okay. Is it like, say, HA, there's Hilbert space corresponding to A, where A is my reference frame. Let's start with that.
Sorry, which one?
So you have written this tensor product, HA, HB, right?
Which one?
Yeah.
Yeah.
So my reference frame, like, as you said, that I can switch my reference frame to B also. And for that, HA will be my quantum object, right? Where its dynamics I'm looking at. I want to understand this concept now. Like, so now observer and the quantum system, they both are propagating with unitary. I mean, it is evolving unitarily, right?
So here I haven't introduced any dynamics yet. I'm just talking about the kinematical level where I have a quantum state and some operators acting on it, but there is no dynamics yet. We're going to see that next, but I haven't introduced it so far.
Okay, well, I'll wait then.
Okay, you can ask me later if you...
Yeah.
Okay, so okay, this is the group. Now, dynamics. So far, everything is I haven't introduced any Hamiltonian of the quantum systems. But now I also want to have a Hamiltonian description because I want to allow both A and B to evolve in time. So now let's consider a situation in which I start from C and I want to go to A. And B is just the system that they both describe, just as a comparison. And now I start from a Schrödinger equation in C's reference frame, which has this form. So it has a state of A and B and the Hamiltonian of A and B. So the sense in which this is more general than when we take a usual reference frame transformation is that there we would not include the Hamiltonian of the reference frame, but only of the system that we're describing. But here also the reference frame is dynamical. And now to change to the quantum reference frame of A, we apply a unitary transformation S that does not need to be the one that you saw a few slides ago, the transformation to relative coordinates. Let's imagine that this is just an arbitrary unitary transformation for now. And now I just plug these on inside the Schrödinger equation, and I rewrite the Schrödinger equation in terms of the new quantum state and Hamiltonian. So I find that, as it should be when I apply a unitary transformation, I still find a Schrödinger equation, but I have to transform the quantum state unitarily in this way and the Hamiltonian in this way. And notice that this is exactly the same form that I was obtaining when I just apply blindly a unitary transformation to the quantum state and I calculate the new Hamiltonian. It just lives on two Hilbert spaces, but the form is just the same, as it should be. But now we define an extended symmetry transformation as a transformation that, given an initial Hamiltonian of A and B that depends on the mass, the position, and the momentum of the quantum systems A and B, maps this through this relation into the Hamiltonian with the same functional form, but with all labels A swapped to label C. So wherever I had the mass of A, I write the mass of C. Wherever I had the position of A, I write the position of C. Wherever I had the momentum of A, I write the momentum of C. So that's just our definition. Let us see what, and we find two generalizations of the translation and boost transformation that do this trick. I'm going to show you one now. So let's take the simplest example, that is the superposition of translations. So operationally, what this means is that we identify the quantum state of system A at time 0 as the center of our new quantum reference frame. So let's take at some time x equal to 0, this time is arbitrary, but let's just decide that it's equal to 0. The state of A is to be in x1 plus x2. And this defines the origin of our new quantum reference frame. And then the state of B is anything. And let us take as initial Hamiltonian the free particle Hamiltonian for A and B. Now, this is the transformation that generalizes the reference frame transformation. Now, to understand what this does physically, you should imagine we are in the Schrödinger picture here. So with the quantum state evolving and the operators independent of time, imagine that I am applying this transformation to the quantum state. Now, this will be the quantum state of A and B at time t. This term evolves the quantum state of A back to time 0. Here, I change to relative coordinates when A is at time 0. So I compare B at time t, I refer all the position of B at time t to the position of A at time 0. That's where I center my quantum reference frame. And then I re-evolve it forward with the new Hamiltonian. This might sound strange, but actually, when you look at the group representation that I showed you before, this is actually very intuitive, because this is just the product of some elements of the group that I showed you, because this is just what substitutes the time translation in the quantum reference frame A. This is the equivalent of the transformation to relative coordinates, so the translation operator in quantum reference frames, and this is again the new Hamiltonian. But of course, now we change to the quantum reference frame of C, so we have to add the time evolution, so the time translation operator in the new quantum reference frame.
But why is that the Hamiltonian, the one that says H, A, B, and up C?
H, A, B, where?
Yeah, well, the Hamiltonian that you have there in the right top corner.
We choose it to be like that because here we want to define a superposition of translations, and in standard quantum mechanics, the free particle Hamiltonian is invariant under translations. So we wanted to pick a Hamiltonian that made sense. Picking a Hamiltonian that is not invariant under translations to start with will never give us a Hamiltonian that is invariant under superpositions of translations.
Okay, but there are still three systems here, right? A, B, and C. So this is the Hamiltonian
from
Of
C.
C, yes, that
A
C
and B.
sees that
Yeah.
A and B are moving.
So
Okay.
C does not describe itself. C describes A and B. So you take the Hamiltonian of A and B from the perspective of C.
Okay. Yeah. Thank you.
Then if you apply this, so if you change this Hamiltonian using this transformation, what you get is again a free particle Hamiltonian, but you see all labels A are swapped now to label C. And here I'm just using pi instead of p, just not to confuse it with the operators in this reference frame. And so this is the sense in which we define this as an extension of the symmetry transformation. Okay. So let me just conclude this with taking a step back and say, like, what are we doing so far? So we start from a Galilean quantum system. So I haven't included any gravity so far. Then we have devised a quantum reference frame transformation that generalizes the standard reference frame transformation, that connects operationally to quantities that are well defined in the lab. And now we would like to generalize it to gravitational scenarios, and we still do, and this is still mostly an open question. So, and in quantum gravity, there are also, there is literature that also says that we should consider some quantum reference frames. Now, it is not clear what the quantum reference frames that are discussed, or quantum reference systems that are discussed in quantum gravities are related to these quantum reference frames. And that's actually an interesting question in which one could look at. And, but at least it's some connection between the two fields, where from like in the independent perspectives, both came to this conclusion. And also, I think it would also be interesting to connect this for the formulations in different fields, because one good thing that we have here in this formulation is that, of course, it's much simpler, but this means that it's also easy to relate this to quantities that are well defined in the laboratory. So understanding the relation between these, the different formulations that we currently have can give us also some intuition of what we can actually observe in the laboratory, or even if it's just first principle and we cannot actually do that now, but at least we have some grasp of the physical situation. Now, yeah.
I have a question on the previous slide, on slide 13, when you were defining the time-dependent transformations. Yeah, so from my classical intuition, so one way that I could think of implement time-dependent transformations would be, instead of thinking in the Schrödinger picture, to think in the Heisenberg picture. So classically, I would use time-dependent operators, x of t and pb of t, and then try to do the transformation of those. I don't know if it would be equivalent to doing it like this. If it is, it doesn't sound obvious at all.
Yeah, so that's a calculation that I have done. I don't remember if it's in the paper now, but okay. But so one, if you take the Heisenberg picture, then you have to transform. So there is a well-known relation between the Schrödinger and Heisenberg picture. So it means that you have to, so the state does not evolve, then you put all the evolution on the observables. But this means that also this transformation has to be changed. So if I remember correctly, when you describe everything in the Schrödinger picture and you do all the calculation properly, then what you obtain is that this term and this term drops, and you're just left with this central term here for the transformation. And that's it.
Okay. Well, a further question, in the Schrödinger picture, would it be equivalent to do this translation in a fixed time, say different from t equals 0, t equals t star?
Yeah.
Okay.
That's actually the way it's written in the paper at some arbitrary t star.
Yeah, I have actually read the paper and tried to work the calculations, but it still wasn't obvious to me. So,
okay. Yeah, no, the time is arbitrary. You can just take any T star.
Okay, thanks.
Okay, so now I promised you that I would also derive the same transformation, so that this simple transformation to relative coordinates from another perspective, where the relational character and why these variables are actually the meaningful relational one is a bit more transparent. And to do that, we're going to use again a very simple model, a 1D model of n particles that interact via an pairwise interacting potential. So now what we want to say is that this system is invariant under global translations. So this basically means that if I have these n particles along the line, I can take this system and put it here or put it here. I can just globally translate it and the physics doesn't change. How do I write that formally? I write that by adding a constraint that is the total momentum. And I say that this total momentum is equal to 0. So classically, of course, there's no problem. If I want to impose that at a quantum level, there is a little bit more work to do. How do I do that? So first I ask, so I write a general state. So for those of you who are familiar with constraints, I write general state will be in a bigger Hilbert space, that is the kinematical Hilbert space. And then I have to reduce to the physical Hilbert space, that is the Hilbert space in which the constraint is satisfied. And to do that, I just impose the constraint on the physical state. So this is basically the same as I was doing in the Page and Wooter's formulation, just a little bit more complicated because this is with P and the other one was easier. If I do that, I can formally write the state exactly like in the Page and Wooter formulation in this way. And this is the state that has 0 total angular momentum. And let's remember for now that this is called also a coherent group averaging. Then this is not enough. So because here I have just basically this information that the total momentum is 0 is just distributed in the state somehow, but it's not evident, at least if I want to reduce how to do that. So basically what I want to do now is to shift all the information, all the redundancy of this state, because this is a state that has some redundancy, on one single Hilbert space. And so what I do is I apply this operator that we call a trivialization operator to the state, to the physical state. And I do that, so I come up with this operator so that now I shift all the redundancy on the Hilbert space of A, and so I have a state with PA equal to 0 and some relative state. At this point, this will be the relative state. And then my work is not over yet, because I still have to get rid of this redundant information. And I do that by projecting on the classical gauge condition. So if you look at this, so this projector is basically xa equal to 0. So this is the momentum that is totally dispersed, which is equivalent on having xa equal to 0. So what am I doing here? I'm imposing that the total momentum is 0. I'm trivializing the constraint. So I'm just mapping all the redundancy on the degree of freedom that I want to get rid of. And then I'm projecting on xa equal to 0, which is basically which means physically I'm centering my quantum reference frame in the origin of xa. So I have these 3 systems that are like a bit everywhere, and then just imagine I put a stick on top of xa, I fix that to be at xa equal to 0, and all the rest is described from this point of view. So at that point, all the other positions that I describe are always referred to xa being at 0. So they're actually the relative observables, and you can check that also mathematically, that all the positions are actually the relative positions to A. And these will be my Dirac observables. And now I can do the same trick, but taking another particle as my origin. And if I want to map directly from this Hilbert space, so from the reduced perspective to another reduced perspective of another particle, the transformation that I find is exactly the one that I derived. You remember at the beginning by saying, okay, let's just superpose the translation, let's apply quantum mechanics linearly and everything else. And I find with this procedure exactly the same transformation. Okay. Now, I just want to briefly mention that there is another approach in quantum information when instead of doing a coherent group averaging, we do an incoherent group averaging. So this may be just for the people who have heard about this before. And so basically there are different ways in which I can make quantities relational. And the connection was found in this paper here, where I assume that there is some symmetry group on some general Hilbert space. And then there is a way in which I define invariant observables that has this condition here. So for instance, this will be the invariance under global translations. And relational observables of the type that I defined so far are instead these ones here, where the total momentum is constrained to 0. And now you will see that so in this paper, they showed that when I just consider this type of invariance, this defines a loser condition. So it's more general, if you want, condition that turns into the, so in terms of the, maybe let's consider the example of the total momentum that is a little bit more intuitive. So it's as if instead of considering only the total momentum equal to 0, that defines what I have done here and what I did in the previous slide. So it's just this particular Hilbert space. I have a direct sum decomposition into different sectors, each of which has some momentum that is different to 0. And these invariant observables basically allow the total momentum to, so they still want the total momentum to be conserved, but it can be different from 0. While this procedure that I highlighted before only says, no, my actual relational observables are just the ones that are where the total momentum is equal to 0. So taking all this set would correspond to the usual way in which relationality is imposed in the quantum information approach to quantum reference frames. And instead, taking only this part of the Hilbert space would be the procedure that I told you about before. So in my opinion, these are two different physical, these correspond to different physical situations. I do not have time to go into that, but if you're interested, you can read this paper. Okay. Now, maybe we can have a break here and.
All right. If anyone has any question, please raise your hand and I can unmute you.
I have a question. Oh.
Yeah.
So for in the slide before, so how do you, well, in both sides, so in the relational and in the other side, you put an operator U that encodes some, well, some symmetry, some constraint, but is it obvious how to obtain the operator in one side and in the other such that you will get the same subspace embedded into the bigger subspace?
So this is something that you usually start with. So you're saying, okay, for instance, my system is invariant under translations, it's invariant under rotations, it's invariant okay, you can have different groups. For instance, here they consider all sorts of discrete groups. So
okay, so it's only going to be like the restriction.
Yeah.
Okay.
I have a question. If instead of a pure state you consider a mixed state, and your observable is the von Neumann entropy. You call this an observable. Does it transform? I mean, considering that, as you show entanglement, on the one hand, entanglement is not invariant under frame transformations. On the other hand, the experiment also has to be transformed. It's plausible to me that the von Neumann entropy is invariant under quantum reference frame transformations, but it's not obvious. Has this been checked?
No, so the entropy has not been checked, but you should also assume at least some sort of like set of observables when you want to compute that, like at least what are the accessible observables to you also when you calculate the von Neumann entropy. So but I don't know, I haven't done the calculation, so.
Thanks.
I have a question. Are these relational observable states, are they anyway related to relational interpretation of Carlo Rovelli, or are completely independent of those things?
So the flavor is the relational is the relational flavor.
Okay.
I think that there is a lot of debate currently on the relational interpretation, and this involves mainly the measurement. So here we try to avoid this problem.
Okay.
And because we were more interested in giving setting up a relational formalism without going into the measurement problem, that is a whole other matter. For sure, like the core is a relational core, and it's in line with any relational approach that you can, or relational interpretation, and various versions of the relational interpretation.
Got it. Thank you.
We have tried also at the beginning, we were trying to say something about the Wigner's friend thought experiment with this, but it doesn't help because, well, the problem is that there is imbalance of information in both in the two quantum reference frames. And this problem stays. So it's not a problem of how you map observables. At the beginning, we were hoping that we could say a little something at least on that. But at least in the first naive application of the formalism, you cannot. But yeah, we do not know.
Thank you.
Okay, maybe I can move on. Okay, so now let us consider now what happens in space-time. So I wanted to show you this because this connects a little bit also to the things that we said yesterday on the page on waters. So now I want to consider a setup in which we have quantum clocks. Now we have learned that these quantum clocks have internal and external degrees of freedom, and we should consider both of them in general. And we want to put them in space-time. And we also want to allow them to be in some gravitational field. So now, in this formalism, then, maybe first thing to say is that, so here I used maybe something that some of you might be familiar with, which is the covariant quantum mechanics that on which, for instance, Carlo Rovelli has also worked on from the 90s onwards. So this means that one describes the dynamical evolution in the constrained picture. So instead of having some Schrödinger equation, you define a constraint that encodes the dynamical evolution. So you can imagine that as a dispersion relation. And then and this is done by introducing a redundancy. And then you can get rid of this redundancy and find again the usual dynamical law. So for instance, here you introduce some operator P0 that is conjugated to some operator X0. And now if you set this to 1, then you immediately recognize that if you if you annihilate this state by a constraint, you immediately find the Hamiltonian of the free particle in the Galilean picture. And even if you add this G00 now, you can recover the one with the Newton potential, basically. So basically this constraint Ci encodes the dispersion relation for the single clock, external degrees of freedom. And then we have additional, and this is for every clock. So you can consider n clocks and you have n of these constraints. And then you have two additional constraints. So this is a 1+1 description where, let's see that. So this constrains the total energy because this has the P0, that is the total, the energy of the external degrees of freedom. And this is the energy of the internal degrees of freedom of the clocks, rescaled by the time dilation factor that you have to do because, so HI is the energy in the rest frame. If you boost to an additional frame, then you have to consider also these other, these factors. So here I'm assuming that the velocity is very low compared to the speed of light. So it would be the tau dot of the clock otherwise. And so this is very reminiscent of the Page and Wouters formulation, where they just constrained HI, so the sum of all the HIs to be 0. And here, in addition, I'm adding the external degrees of freedom. And this thing here is the conservation of the total momentum. And this is basically the same that we had in this perspective neutral formulation that I showed you a couple of slides ago. So now we want to put all these things together. And there is an analogous procedure. Okay, so this is the conservation of the 4 momentum, basically, if you had a 3+1 picture. So in this case, it's the 2 momentum. So now we can build an analogous reduction procedure to the one that I showed you in the one-dimensional case where only the total momentum was conserved and constrained to 0. Here we have an analogous, perfectly analogous operator to reduce to the perspective of one single clock, where the time evolution is given in the internal Hilbert, basically the proper time of the single clock. And this single clock describes all the other clocks in its proper time and assigns some Hamiltonian that you can write as the external Hamiltonian of the other clocks, plus this would be the tau dot times the Hamiltonian, the internal Hamiltonian of the other clocks. Okay, and this is what I said. And this has the gravitation, this encodes the gravitational time dilation. That here, this G00 is in the Newtonian limit, so you can express it in this way. And this is basically the distance between the each clock with the mass that is sourced in the gravitational field. So what can you do with this? So imagine that you have an atom, a clock, and you put it in an interferometer. So now let's go back to the clock lecture yesterday. We have the Earth, and we have a clock that is inertial, so it's on the surface of the Earth. And then you have another clock that goes in a quantum superposition of 2 paths. So now, one thing that you can check is that when the time of this clock is well defined, we have seen already that there is a reduction of visibility for a clock that is inside an interferometer in a superposition at different heights in the Newton potential. But now you can also go in this formalism to the quantum reference frame of this clock and look at what this other clock does. And you will observe exactly the opposite effect. So this clock will tick according to some time, while this clock will tick in a quantum superposition of times. And now, instead, you can also put these 2 clocks together in a quantum superposition, always at the same height. So either they both go here along this path, or they both go here along this path. And now, if you take the perspective of the orange clock will see the blue clock as always telling the same time. So we have a similar relative localization of events as for the interacting clocks, but in this case, we take a different formulation where we also take into account the dispersion in space, so the quantum state of the clocks in space-time. And if you go a little bit even wilder, then you can also come up with a generalization of the Einstein equivalence principle in quantum reference frames. And the easiest thing to do is to just come up with a test in the classical gravitational potential of the Earth, where you put clocks in a quantum superposition. And there you can formulate a quantum reference frame transformation to the quantum reference frame of each one of the clocks that is in a quantum superposition in the interferometer, and verify that you can make the metric locally Minkowskian at the position of these clocks. And if you use this formulation that I showed you one slide ago, this is done in this paper, then you show that if this Einstein equivalence principle for quantum reference frame is not valid, it doesn't even make sense to define time evolution in a quantum reference frame of these clocks. So there are very heavy consequences if this is violated. Because basically, so you, in referring to the Page and Wouters formulation that I told you about yesterday, basically you do not even get to defining a history state for the Page and Wouters. And then you can also consider a superposition of gravitational fields. And again, you can go to the quantum reference frame of a particle that is entangled with this gravitational field and define a quantum reference frame transformation and show that it takes you to, we call it quantum local inertial frame, where the metric can be made locally Minkowskian at the origin of the quantum reference frame, regardless of the gravitational field that was in a superposition at the beginning. So you basically define a quantum superposition of transformations to a local inertial frame in this picture. And we have related that with the Penrose spontaneous state reduction. And so I told you 2 lectures ago that he argued in terms of these 2 principles of Einstein's equivalence principle and principle of linear superposition, which are not compatible. And then he wanted to put general relativity first, so he gave up the principle of linear superposition and came up with this spontaneous state reduction. But here, what we are saying is that actually, if you're ready to generalize the Einstein equivalence principle, then you can keep both, and they're not necessarily in contradiction. And now, the last thing that I wanted to tell you in these lectures is, now I want to, so this is a speculation, and this is something that we have not yet fully worked out, it's just an idea. Can we say that the superposition of gravitational fields is a relative concept in the same way in which entanglement and superposition are a relative concept in the Galilean version of quantum reference frames? And we have applied this to an experiment that is called the gravitational Aharonov-Bohm experiment. And so let me just briefly describe you what this experiment is. So this is an atom interferometer that has been done in Stanford in the group of Mark Kasevich, and it's from last year. So an atom interferometer is an interferometer, so like the ones that I described. And in this case, this is placed vertically in the gravitational field of the Earth. So you have to imagine a cylinder that is 10 meters high, and that basically at the bottom of the cylinder, there is a source that shoots atoms up. These are single atoms. And these atoms have a wave packet that is split, and it reaches a highest point and then falls back and it's recombined, and to measure interference. And in this case, the distance between the two arms of the interferometer is 25 centimeters. So you can simplify this description. So this is a very complicated description. This blue particle in particular, they need it for the experiment. As theorists, we don't need to worry about that. So in the freely falling frame, you can describe this interferometer as, so A is the particle, S is the source. What is the source? This source is this half donut here. It's a tungsten mass, which weighs 1 kilo, and it's placed on top of the interferometer. And the design of this experiment is extremely careful, so that basically at the highest point, this particle goes really, really, really close to this half donut, to the tungsten mass. So what they measured is the gravitational interaction between the tungsten and the atom that is sent up in the interferometer. So basically, this experiment is done in such a way that the gravitational field of the Earth factorizes out. So you don't measure any effect of the gravitational field of the Earth, but you measure the difference in which the source acts on this arm of the interferometer, on this arm of the interferometer. And in particular, this turns out to be a relative phase at the end of the interferometer. That is the difference between the potential, the gravitational potential sourced by the tungsten mass in the two arms. And so the major advancement that they made in this test is that so far, atom interferometers had only probed the uniform field approximation. So basically the potential mgx. Here they go beyond that. So they take the next order in perturbation theory. So it's an extremely sensitive experiment. And now what we wondered is with them is, let's take everything that we know from current experiments. So what do we know? We know that localized masses as light as 90 milligrams source a gravitational field. So also the tungsten mass sources a gravitational field, they have measured it, but even masses that are smaller than that. Then we know that the equivalence principle is valid up to experimental resolution. Then we know that there are gravitational waves. And then from this experiment, we know that there is a gravitational phase shift between the different paths of an atom interferometer. And then we know that classical gravity, basically the tungsten source, and quantum theory are compatible beyond the linear regime. So this experiment can be explained as it is with classical gravity. What elements are we missing to test in order to have a superposition of gravitational fields? And we came up with some assumptions that yet have to be tested. And these in particular, so there are 3 assumptions here. I just want to focus on 2. One is the existence of gravitational fields that basically tells us that every localized particle, regardless of its mass, is the source of a gravitational field. That where by gravitational field, we mean gravitational field in the sense of like field theory. And second is the quantum relativity principle, stating that the laws of physics are the same in every quantum reference frame. So in this sense, if you take these 2 assumptions and you map to the description of the atom, then the picture that you will observe is the atom being in a fixed position and the source, so the tungsten, being in a quantum superposition. And so now, if the laws of physics have to be the same, then you have to conclude that also the tungsten source, in this case, sources a gravitational field. And that the gravitational field is actually a relation between this tungsten source and the atom. And that's the one that we measure. So now, this is not to say that this experiment proves that the gravitational field is in a quantum superposition, but this gives you some first principle compatibility between quantum theory and general relativity. So here what we're trying to do is to stretch to the extreme the consequences of taking all the first principles from one theory, the principles from another theory, put them together and test them in a concrete physical situation. And it is still an open question, up to which point this will be true, how much we can deduce from this type of reasoning and this type of, well, now thought experiments, and hopefully they will become real experiments in the future. So to summarize what I've said so far in this lecture, I have introduced an operational and relational formalism for quantum reference frames, which means that we want to associate a reference frame to a quantum system. In quantum mechanics, we have seen that this leads to a frame dependence of entanglement and superposition, to the generalization of the notion of covariance, and I didn't show you explicitly these 2 points, the generalization of the weak equivalence principle and an operational definition of a rest frame of a quantum system. I didn't cover that. In gravity, we have seen that this can generalize the Einstein equivalence principle and how this is related to Penrose decoherence. Now, in quantum gravity, we cannot have a classical reference frame, and the hope is now to take this approach and use a bottom-up approach towards non-classical spacetime to include the need for quantum reference frames in scenarios when the spacetime is no longer classical. And this is a vastly unexplored research field. There are many open questions, which also means a lot of work to do. Now, let me just close this set of lectures by telling you some, so I've talked about many different things that might seem unrelated. So what I tried to do is to come up with some relation between these different topics. So we have seen in the first lecture the theory-independent approach, so generalized probabilistic theory, and quantum causality with process matrices in particular. Then in the second lecture, we have seen gravitating quantum sources, so gravitational quantum sources, and no classical spacetime arising from them. Then we have also seen quantum clocks yesterday, and today quantum reference frames. So of course I had to fit the different topics in one or the other lecture just because I had to, but there are many connections between them. So we have seen that explicitly for process matrices that they are something, so they're a framework to describe indefinite causal structures in a theory-independent way. We have also seen in the second lecture no-go theorems that use explicitly generalized probabilistic theories to talk about the quantum and gravity interface. Now we have seen this gravitational Aharonov-Bohm effect, where we would like to connect quantum reference frames to this field of having gravitational, so a quantum source of gravity via these transformations. And clearly the gravitational Aharonov-Bohm experiment is an interferometer. Quantum clocks also, through spacetime quantum reference frames, are this is a topic that connects both these topics that I've discussed. And if we use Page and Woodard's description, and also in particular the relative localization of events, so basically these interacting quantum clocks via gravity we call them sometimes temporal quantum reference frames. So they also connect to the topic that we discussed today, and to non-classical spacetime, because via the mass energy equivalence. And then, what am I forgetting? The equivalence principle that was formulated in terms of quantum reference frame, but of course it also has a lot to do with non-classical spacetime and with quantum clocks that in the end will be how this is going to be verified. And the gravitational switch also connects many of these topics, because it's a quantum superposition of causal order, so it's a quantum switch. And it also connects to quantum reference frames, because you the mass is in a you can go to the frame of these local observers A and B, through the clock picture that I showed you, and to non-classical spacetime, of course. And I haven't told you about that, but actually the paper of the gravitational switch was formulated so that the title is Bell's theorem for temporal order. So they gave a theory-independent argument for the superposition of causal orders in this case. So there are really many connections between among all these topics that I discussed. And now you will see that there are also some missing links, and these are also the links that we should fill somehow to find more connections and more discussions. And yeah, and so just to conclude this set of lectures, I have outlined several topics and that all follow some methods. So the methodology is shared among all these topics that I've covered, and this broadly characterizes the field of quantum foundations. And the way I see that is, so the way I see this characterization is through three different elements. First, to establish a connection between first principles and the mathematical structures of the theory. Second, to develop tools to systematically test the internal consistency of the theory, and this can be done via quantum information protocols, no-go theorems, generalized probabilistic theories, and so on. And finally, to operationally define the elements of the theory in terms of laboratory procedures. Now, for the future, some questions that we can ask is what limits this approach? How do we, for instance, the measurement is usually a very critical problem in quantum theory, the measurement problem. And also, we are trying to build up our way to include more and more gravitational aspects into this research. And then one can ask if also there we will have to stop at some point, or how much we can extrapolate, and how to connect it and how to improve this method by integrating it with more traditional quantum gravity research. And these are all open questions that I'm happy to discuss. And yeah, and I'm also happy to take questions. And with this, I would like to thank you all for your attention and for giving me the opportunity of talking about all this research in these 4 lectures that have been very instructive for me too.
Thank you for taking the time to review all those topics in a very pedagogical way. Now we have time for questions, of course. We have already 2. Let me unmute people.
Hello. First of all, thanks again for a really great set of lectures. I mean, these are difficult topics, and I've never heard them explained in such a great way. I mean, seriously, thanks. Regarding the gravitational Aharonov-Bohm effect, this is indeed a really interesting experiment, and it's interesting that you explain it with quantum reference frames. I mean, this goes back to the question about entropy, because what do you call it? The thing of tungsten is an object with finite entropy. It's completely decohered, and it has pointer variables. I mean, you know, there is no entanglement there. While the paths have no set of pointer variables, they're entangled. So can I take it as a demonstration that at least, I mean, pointer variables are sort of quantitative things. If it depends on by how much they commute with the heat bath. It's the commutation between the heat bath and the system. So do I take it as an indication that sort of, if you want, change in reference frames could blow up pointer variables or drastically shrink pointer variables, in the sense that one system is nearly pure, the other system is nearly maximally mixed, and you can sort of interchange them between changing reference frames, but the system is invariant. I mean, the fact that the fact that you have such mixing is sort of invariant for the observables. You see what I'm saying?
No, I'm not sure I understand the question.
I mean, from the point of view, if you think the particles are superimposed, the cold atoms are superimposed, that's okay. It's a highly pure microscopic quantum system. But the tungsten thing being superimposed, that's really a Schrodinger cut state. Because the tungsten thing, it has an entropy and it's maximally mixed. And so you're going from the reference frame transforms between a nearly pure, a superposition of a nearly pure state to a superposition of a nearly mixed state. And that has no observational consequences.
Well, I mean, if the state of the tungsten is maximally mixed, then this is something that I can take into account in my initial description, right? So,
I mean, the fact that it's maximally mixed, just to say, doesn't actually mean that you can't have superposition. It's just that the superposition is, you know, Bayesian ignorance. I don't know where the tungsten is.
well, but you know where the
Quantum superposition is a different thing.
They have it in their lab. They can control that pretty well.
Yeah, but if you are looking at it from the reference frame of the atom, you don't know.
Mm-hmm.
If you're sitting on an atom, which is superimposed, and you are taking it as a quantum reference frame,
yeah,
you know,
then you would see
that. Yeah.
And you would see the tungsten as being in a quantum superposition. Yeah.
But is it still a quantum superposition or sort of a stochastic superposition? Because superimposing a tungsten is very different from superimposing an atom. That's sort of.
I agree. Yeah, I agree.
All right. Thanks.
Yeah, hi. Thanks a lot for your work and sort of gathering everything together for us. You've given me at least a lot to think about and a lot of browser tabs to work through over the coming weeks or discard in a couple of months. But I want to go back to the Asenbaum experiment. The way I read about it, and I've read about it, both the gravitational one and the electromagnetic one previously, was they were sort of establishing the ontology of a potential instead of just the field. Did they also view it from this sort of like superposition quantum mechanical point of view, or?
So there are some papers that think about this in terms of the quantum superposition. I think that there are some papers by Lev Weidman on the electromagnetic Aharonov-Bohm effect that view it in from the perspective of the quantum superposition. So at least he considers the relation, like he makes some relational considerations.
So, but that is like not the general way that they conceive of the experiment. The experiment is mainly in the ontology of the potential, right?
So yeah, that's
we can, of course, we cannot read their minds, but like in the papers, they've not like mentioned it or like given a reference to it. At least the one I like skimmed the one about the gravitational version.
But sorry, you mean the original one, of the Kasevich group?
Yes.
Yeah.
That one. I don't remember them mentioning this sort of like quantum relational, quantum reference frame sort of point of view.
So that's a follow-up paper that we have with them.
Okay. Oh, okay.
Yeah. Yeah. So at the beginning, yeah, they just did it in the standard gravitational Aharonov-Bohm picture. So and then that's a follow-up paper that. Yeah.
Okay. Then maybe I can ask you a question about like, is there an experiment you are looking forward to in the near future that you're always like Googling over and over? Do you see, like, are the results in yet, or? Yeah.
So in the near future, it's hard because this. Of course, like, okay. what I would really like to see realized is an experiment showing that the gravitational field is actually in a state. But that's, I mean, I cannot Google for it every day because I know that experiments are still pretty far from that.
Yeah, I was more wondering, is there an experiment that you know is being done? Is like there's a lab out there somewhere that's doing an experiment that you're really excited about, or
No,
are you
okay,
more
so
excited about? Is it more
experiment-
like ones that are being in the design phase that you're excited about?
Yeah, so no, this for sure. So there are both like so all these groups that I mentioned at the beginning, like for instance, Marcus Aspelmayer, Mark Kasevich, they're improving orders of magnitude in their setup. So and these are experiments that they are doing now, and so yeah, I'm looking forward to seeing these results. Out.
Yeah, maybe they get a negative result all of a sudden, and then everything's in the air.
Yeah.
Okay.
Not, but
yeah. Well, you hope and you hope not, and like it would be more exciting, I guess.
Yeah.
But
Okay. There will be a lot of work for
annoying.
everyone. But these experiments find something surprising, but
yeah. Okay. Thanks.
So thanks again for the wonderful lectures. I have sort of more broad conceptual questions regarding the end of your presentation. So I myself have a quantum field theoretical background, and while I find this formalism very nice and this idea of coherent translations and taking this relational approach to reference systems, it sounds very puzzling to me how one could conceive of generalizing them into relativistic situations. And in one sense, because so in relativistic quantum mechanics, you no longer have position operators well defined, for example, and then it becomes trouble how you translate into some reference frame. And furthermore, it seems even more complicated when you try to go to a field theory perspective, right? Where your observables are field amplitudes towards space and points of space-time. So I was just wondering if you have general comments and thoughts on that.
Yeah, so this is a question that we have asked for a long time. So, and there are people who are thinking about that now. But I do not know the details. So definitely, when one wants to go more towards a quantum field theory perspective, then there are some pretty substantial things that have to change in the formalism. So initially, we started in this Galilean picture just because it was easier, and it allowed us to conceptualize many things without really having all the problems that special relativistic quantum mechanics and quantum field theory would bring us. And then the idea was to like slowly build up our way towards generalizations of the formalism. So this is not to say that, so that's why I said at the beginning that many things will change on the way, and this is just a starting point. And for instance, one of the things is, yeah, the notion of the quantum preference frame to identify the correct relational variables, and okay, also the locality. So the idea towards which we are as a community, I think more or less all going now, is to not define, so to define things as in terms of the interaction, so to have more a relational picture in terms of interactions between two physical systems rather than really localization in space-time. And interactions is something that you can define a little bit more meaningfully, even in the quantum picture. So that's one possibility, but it's a very general idea and long-term project. So I don't know how much more concrete I can be on that, because I don't know it myself.
Yeah, all right. Just wanted to hear some thoughts on what directions these things were going. I myself am very interested in those. So, well, thanks again.
There was a question in the Q&A, Flaminia.
Okay.
You might want to have a look.
Does quantum reference frame mean a quantum state of spacetime can be constructed with quantum reference frame transformation? I'm a little bit confused. No, so this is not what I'm saying. So far, we are just taking different perspectives, and a quantum reference frame transformation is just a change of description. Then if you want to relate this to to construct with a quantum state of space-time, so maybe the confusion comes from the fact that I said is a gravitational field superposition also relative to the quantum reference frame. And then this is just a very vague idea that I expect. So for instance, mapping a gravitational field in a quantum superposition into a definite one will be something that will only happen in some very particular cases and not in general. So I don't expect this to hold as a general rule, but it can still help to build up our intuition in some specific situations. That's something that I think can happen.
So I have a question, that maybe is related to this. So, well, here in Radboud in Nijmegen, so we work with random geometries, right? So I am always looking for the random geometry, where the random geometries could appear in quantum gravity. And for me, it seems like something that if you have these transformations, these operators that transform your metric to make it flat and non-flat locally, at least. I mean, it seems for me that in principle, you should be able to give an expression for how the metric is gonna evolve or how it is gonna look, at least locally, with these transformations. Is it something that has been done or tried, or why it's harder maybe?
Yeah, so far we only have it for superposition of classical diffeomorphisms. So that's a very specific case, and if you want, also pretty intuitive, because you just take a diffeomorphism and then apply it in a quantum superposition. And that's all we have. And we do not know. And so the trick is that in this case is also the states of the gravitational field should be orthogonal one to the other, which is not the most general case, of course.
Yeah.
So it's still a relatively simple case. And we do not know what happens for more complicated situations. And this would be interesting.
Yeah, what is the main reason why you are not able to do it in more general cases? Is it just operationally, or?
Yeah, it just Okay. We have to build up the formalism for that.
Okay.
Yeah.
Well, but that sounds very nice.
I have a question that is sort of a follow-up to the previous question about the entropy and the pointer states of the macroscopic versus the microscopic object. It seems to me that then sort of the entropy and mixedness would become a relative to your reference frame. Is it general that most quantities become relative, or what are the sort of invariant quantities with these shifts in reference frames?
Okay, it depends.
Of course.
The answer is always it depends. So the probabilities, once you fix the experiment, are invariant. And then for each type of transformation, you will have some invariant quantities. But if you change the transformation, then you will have different invariant quantities.
So if you were to take the most general transformation, which could be a product of many transformations, you could say that there are no invariants. Or do they have any invariants in common?
I don't know. One should
No.
really check case by case. I haven't.
Yeah.
I haven't done the general calculation. But for instance,
Okay.
of course, like for instance, if you take the translation, then of course the momentum is going to be invariant. Or
Yeah.
So
But then you take like rotation, and then everything goes.
Yeah.
Yeah.
the angular momentum, then yeah.
Yeah. Okay. Yeah, it's a pain in the ass, isn't it? Okay.
Yes.
I was just wondering if like something would very nicely fall out of the sort of group theory point of view, because then you could maybe
Yeah.
like say, aha, there's this one part of it that works out, but I guess not.
Well, so there are some, I think in the paper we have some Casimir of the algebra, so stuff that commutes with everything.
But that
There's
would
a
correspond
horrible
to
expression, a horrible expression.
yeah, although the Casimir, what does the Casimir element like correspond to, like physics?
Yeah, no,
wise?
we do not know.
It
Like,
seems a very abstract sort of like a
Yeah.
thing you put in there to like fix stuff, to make things work again. Right?
Yeah. No,
Ah.
so and this had no explicit physical interpretation. We didn't find it.
Okay.
Just rhetorical.
Okay, thanks.
Hi, this is actually, sorry, this is a follow-up, sort of a follow-up to the previous question. That there is a theorem called the Wigner-Araki-Yanase theorem that basically says that the only possible measurements that can be done in a statistical ensemble that converges to sort of quantum uncertainty relations are those that commute with the Hamiltonian. Are those that commute with the Hamiltonian. You can sort of see how it works, because it's idealization. The experiment has to take an infinitely long time, and that's why there will be additional. Of course, things that whether something commutes with a Hamiltonian or not, in general, becomes dependent on reference frames. If you boost something, if you accelerate something, you can get time dependencies of the Hamiltonian. So in a quantum reference frame scenario where you have a superposition of reference frames, you will also have a superposition of whether something is a good observable or not. Is there a way to characterize this? Just as a
Well, no, like, I mean, you can just, I wouldn't say that there is a superposition of what is a good observable or not.
Sure. Isn't it true that you can make something not commute with the Hamiltonian by changing reference frames?
Well,
even in the Galilean limits, certainly in
this
the
doesn't
Lorentz.
mean that it is in a quantum superposition of commuting or not. It will, if something commutes with the Hamiltonian, it commutes with the Hamiltonian. So it's not in a superposition of commuting or not commuting.
Okay. Thanks. Maybe it was understood.
Okay. Is there any other question? I actually have one question. So when you do those QRF transformations and somehow you enable that you have, or you were able to somehow swap the entanglement that you have across different subsystems, one thing that I never quite understood about what's going on is the fact that you could imagine that those different reference frames, they are instantiated by different physical systems, which can have, of course, very different size of a Hilbert space. And so I would imagine that there is a limitation to the extent in which you can actually do the transformation from one physical system to another, such that the amount of entanglement which is swapped is compatible with the size of the Hilbert spaces that you are changing. Yeah, so how does that work actually?
So usually here we assume that everything is in continuous variables.
Mhm.
So we have an infinite dimensional Hilbert space.
Yeah.
Then you can consider, for instance, particles that have some additional internal degrees of freedom. But typically we would consider them as external systems. So the basic that we need is the continuous variable. And then you just transform between that.
Mhm.
And then all the additional things that you have, you just treat them as external systems.
But so does that mean that in principle it's not easy to carry out the framework into only finite dimensional Hilbert spaces?
Yeah, so at least you wouldn't have the same intuition matching, like you wouldn't match the intuition of the continuous case, yes.
Right, okay, thanks. All right, I guess we don't have any other question. So let me thank you again for those 4 wonderful lectures.
Thanks.
And I think they're going to be, it's really, really a great start for the lecture series to have them there online and to, I think you're going to set a very high bar actually for the next speakers. And yeah, of course. And thanks everyone for joining, for the people who stayed, and for the people who are going to be watching this later as well. I guess you can always leave comments, perhaps on YouTube and interact. And I guess probably Flaminia is also available by email to for the
Yeah, sure.
Yeah, so thanks again.
Thanks to the organizers.
Yeah, thank you, Flaminia. Thank you.
Yeah, thank you so much. It was amazing.
Thanks to you.
So I think, let me double check, both on perturbative quantum gravity and the basics of loop quantum gravity. Actually, they're starting on the end of the first week of June. And they're going to be interpolating between perturbative quantum gravity by John Donog and the basics of loop quantum gravity by Hal Haggard. So yeah, I invite everyone to stay tuned for the incoming lectures. And yeah, thank you everyone again.
Thank you.
Thank you, everyone. Okay.